Hi everyone. I was asked to look at this question recently. It's from the 2007 WACE paper, section 1, question 8. A circular wire loop is placed near a long, straight wire carrying a constant current in the direction shown. The loop moves 3 times. A, it rotates once, uniformly along the x-axis with the resistor R moving out of the page initially. B, it moves parallel to the straight wire with a constant speed. And then C, it moves away perpendicularly from the straight wire with a constant speed. So A, it rotates at this location here. B, we see that the wire moves, or the loop moves vertically upwards. And then C, we see that the loop moves away from the wire. And what we're supposed to do in this question is we're supposed to identify the EMF that might be induced in the wire. We're supposed to graph the EMF induced in the wire against time for each of these changes. And we're supposed to try and figure out if there is a current flowing clockwise, anti-clockwise, or in a way that it's irrelevant for each of those changes, A, B, and C. Before we go too much further, it's worth noting that our current carrying conductor is generating a magnetic field. The magnetic field is into the page on the right-hand side of the conductor and diminishing as we move further away from the conductor. We know this because of our right-hand curl rule, where we use our thumb to follow the current up the wire and our fingers to wrap around the wire. We do this in our imagination, in our mind, and that tells us that the magnetic field from the wire will be into the page on the right, out of the page on the left. In A, the loop rotates once, uniformly along the x-axis, that's the horizontal axis, with the resistor R moving out of the page initially. We remember that the magnetic field is into the page on the right-hand side of the conductor. So we're seeing that in the initial orientation, there is a maximum flux moving through the coil. As the coil goes through its rotation, we are going to see, if we follow the rotation in 90-degree intervals, we are going to see the initial rotation is going to be like so, like we have on the graph. After 90 degrees, we're going to see as the resistor moves out of the page towards us, that the plane of the loop is horizontal and the resistor is close to us. After another 90-degree rotation, we're going to see that the resistor is at the top of the loop. After another 90-degree rotation, we're going to see that once again the plane of the loop is horizontal, but the resistor is now behind the loop. And then the final rotation of 90 degrees, bringing us up to 360-degree rotation, puts the loop back where it started. And we might label these A, B, C, D, and E. And this rotation of the loop reminds us of the behavior of a coil in a generator. So we're going to think to ourselves that the EMF induced here is going to be a sinusoidal wave, like in a generator. So we might draw that in. Where the minimum EMF being induced is happening at A, C, and E, because in these orientations, the plane of the loop is perpendicular to the flux lines. So as it's rotating, there is almost no cutting of flux for A, C, and E. On the other hand, we're going to see maximum flux being cut, therefore a maximum rate of change of flux through the coil in points B and D, because in these points, the plane of the loop is parallel to the field lines. Now, if we had to identify what the direction of the current is in the loop throughout all of these changes, we might consider going from, first of all, we might consider going from A through to B. Now, as we move from A through to B, we're seeing that there's a maximum flux situation in A to a minimum flux situation through the loop in B. Faraday's law tells us that there will be an EMF induced in the loop because of this change that's being observed. Lenz's law tells us that the direction of the current will be such that the loop generates its own flux to try and replace the flux that's being lost. So that would mean flux into the page to try and replace the flux that's being lost. My right-hand curl rule tells me that this can happen if the current is clockwise in that situation. If we followed then the loop from B through to C, from our perspective, looking on the outside as we are, we would see that the loop is experiencing no flux through it in B, and then we see that it is experiencing maximum flux through it in C. Now, from our perspective, looking from this side of the screen, that would make us think that the current will be in such a way as to oppose this change. So the current will be in such a way as to create a flux that is out of the page, not into the page, which is going to be possible from our perspective if the current is flowing in an anti-clockwise fashion from our perspective. But don't forget that the loop at this point has reversed. So that current flow would actually still be in the same direction as we saw from A to B. So from the loop's perspective, as we follow from A through to B through to C, the EMF is always going to be in the same direction. And then as we go from C to D to E, it's going to be in the opposite direction. So if we go to answer this question, do we say clockwise or do we say anti-clockwise? Well, we might say both, or we might say that it is irrelevant. In B, we see that the loop moves parallel to the straight wire at a constant speed. It's moving up. As the loop moves up, we remember that the magnetic field created by the current carrying conductor is uniform as you move up and down, but diminishing as you move left through to right. So in this situation, the loop, if it moves up or down only, it's not going to perceive a change in the magnetic field that's passing through it. And the EMF is dependent upon the idea of a change in the flux that's passing through the loop. If we move only up or down, there's going to be no change in the flux passing through the loop, and so we're going to see no EMF being induced, which gives us a flat line on that graph there. And of course, if there's no EMF induced, there's no current, so we can't say clockwise or anti-clockwise. It would be irrelevant. C. If the loop moves perpendicularly away from the straight wire with a constant speed, then we're going to see that it's moving from a region of dense flux to a region of less dense flux. The flux generated by this coil is described by the equation B is equal to mu0 over 2 pi times I over R. So because of that, we know that flux is equal to B times A. The area of the coil is not changing. So that tells us that the flux, as we move away from the coil, is going to be proportional. The flux is going to be proportional to 1 on R. So if we were to graph the flux as we moved away from the coil, it might look something like this, where we have a tremendous amount of flux close to the wire, and then a very, very small amount of flux as we move further and further to the right of the wire. But it never becomes zero, it just gets smaller and smaller and smaller. So what this tells us, remembering that EMF is related to the change in flux, the rate of change in flux over time, what this tells us is that as we move from the left to the right, moving away from the coil, the speed with which the flux changes and diminishes as we move to the right becomes progressively less. But it never stops changing, it just becomes progressively less as we move to the right. So our EMF that's induced is going to be quite high initially, and then it's going to become less and less and less as we move away. It never actually stops, but it moves to the right. As it moves to the right, it becomes less and less and less. So there's a slight curve there. The direction of the current, when we look at this, is going to be such, Faraday's law tells us that there will be an EMF induced in the coil. Lenz's law tells us that the direction of the current that's being induced by that EMF is going to be such that it wants to replace the EMF that is being lost. That means that the induced EMF is going to generate a current which generates a magnetic field or flux into the page, which is going to happen if our current is moving in a clockwise fashion. I use my right-hand curl rule to be able to figure that out. I want my fingers to go through the coil, and so that means my current has to be clockwise. Okay, I hope this was helpful.